Hi, I'm Jean-Louis Van Bella. I want to do a video in a series that I did a bit on ICT in general. I want to talk about Nvidia. As you saw from the press, it's quite a phenomenon. And I want to do a bit of a fun video. I'm not going to say you should invest in Nvidia or not. There are other sites for that. I want to show you what they're doing and why there's so much of I wouldn't say a hype about it, but yeah, so much talk about it. If you want to invest, then I looked at a few sites. This one, the Motley Fool, I looked at it. It's an investment company apparently with quite some history. And this article is really good. Nvidia versus Taiwan Semiconductor Manufacturing Company, the Taiwanese-based company. It does a comparison of how the share prices of both have exploded literally, partly because of this alliance between Nvidia and the TSMC with the production of these new AI accelerators. I would say we can talk about GPUs. I will say a few things about it, but these are yeah, chips that are designed for very specific artificial intelligence workloads, and so yeah, they're definitely superior to other chips that can handle that. So TSMC went from share sort of tripled. Um, if you look at the share price of Nvidia, that has that's times six or times 10, or times 8, I would say. The article is good because it tells you actually, well, it recommends, and actually NVIDIA is not one of the recommendations in in its investment advice, for which you can consult the site, because it looks at the price to earnings ratio, another one of the many metrics used to assess stock evaluation, and yeah, that price earning ratio for Nvidia is quite high. 55 is the ratio, as opposed to 30 for TSMC. So is it the top of the bottle? I don't know. Should you invest $1,000 in Nvidia right now? That's about the price of a share, one share. Yeah, if you would have invested in Nvidia 10 years ago, yes, then and probably you would have won. I have a bad experience. I'm 55. I invested in Intel 25 years ago in very specific tech companies, and you know, if you don't know the market, which I don't, then you're always too late, and you get in too late, and usually you leave the market too late. But I said I want to make a fun video and talk a little bit about what it's all about. So I made some notes. This is empty here. Um, some funny notes, maybe. These are the notes I made a little bit to explain what NVIDIA does and why there is what its new system is about. To explain that, actually, I wanna do something that I did in previous videos, and is talk about you know, very basic stuff. Um, Today, actually, I took apart my old mobile phone. Um, a Samsung J2 from 2018. It worked fine for me. The problem was really its Android system was no longer being updated. Couldn't accommodate the newer versions of Android. So a number of applications like authentication applications, it's me here in Belgium, didn't run anymore on it. So I could still use it for well, as a mobile phone, and I did. But then last week it was kind of funny. The battery gave up. The battery started, you know, doing weird stuff, becoming bigger. You know, one of these stories indeed that batteries, these lithium batteries, when they overheat, when they're old or they're not properly used, then there's a problem. So I took it apart, and here you can see it. You know, this is the front here. I said this is a phone of like 6 years old. Um, you know, I bought it at the time for I think €200 or €150 basic phone, but with a lot of capabilities. Here you can see the display, and that's sort of the introduction. You know, this display was didn't have the resolution that modern phones have, but pretty good. 540 by 960 pixels, 24-bit, three colors RGB pixels, so real colors. AMOLED activity matrix, so I don't know, but in any case, an OLED screen, a high resolution screen. That technology hasn't changed. Plus a touch screen packed in what Samsung called then the one glass technology. So the only one layer of glass to combine the touch function, the imaging function, and that feeds into a port when you open it up that goes to the GPU, because that's the graphical processing unit that we want to talk about. A lot of other stuff on that phone that was pretty novel. Two cameras, two good cameras, selfie, front, but with higher resolution, 5 megapixels, 8 megapixels. A good speaker, strong LED flashes, and a lot of stuff. The technology was a 28 nanometer. And the funny thing is, and that's one of the reasons that I opened it, is said, wow, such a nice handheld computer. Basically, if I open it up, would I be able to recognize, the parts inside? And I did actually. You can easily, of course, see the cameras and the physical sensors, but really the GPU and the CPU. If I can go to the next page, you can see that here. Yeah, you can open it up, and yeah, you can clearly see sort of that system on a chip, both for the CPU and the GPU. CPU 4 quads, 4 cores. GPU, I will talk about it in a moment, and then sort of the other chips for controlling the SIM card, Wi-Fi, Bluetooth, micro SD memory, all these kind of things, and nicely packaged on a very sweet board. And I was actually surprised because I thought such complicated technology, it's not gonna be like my Commodore 64 at the time 30 years ago, when I would open it up and I would have a bit of trouble understanding its architecture. No, it was easy to understand. Why I'm saying this, because I'm gonna make a comparison between a little bit the what's inside here, and then these new AI processing units, I would call them, GPU, CPU, maybe an NPU now. So they talk data processing unit. I mean, all kinds of new terms, but basically, you have it here. Basically, chipset. Uh, Even in the Commodore 64, you had a video card. That video card, because video has become um, so much better and also so much more voluminous to handle in terms of data streams that go up and down. Um, yeah, a powerful GPU is needed, and CPU is very good at serial processing, at very specific computing task, I would say, at executing logic. For GPU, you need there's a lot of parallel processing going on of indeed video signals that are happening. I have a paper that I want to promote also here a little bit, which I wrote last year, sort of why neural processing units are the next big thing in AI. We know what an NPU is. It's sort of storage of AI use cases, and a lot of these use cases are often with the Internet of Things, like cameras recognizing persons. And I do a few calculations here, and one is indeed, if you have sort of that standard, not ultra high definition, but standard high definition, 1920 by 8 or 1080 pixels, a refresh rate of 60 hertz, which is common, 24 bits for true colors. You have a stream of 3 gigabytes per second, about 375 megabytes per second. You couldn't handle that if there weren't video codecs like AVC or HEVC that compresses video. And so these algorithms run on GPU. And the first GPUs, like in this camera, were not so powerful as well these in this camera here, where we have a CPU, a Snapdragon, and an Adreno 615. Oh, that's actually a later model. I think my phone is a simpler, was a J2, not a J5, from 2015. Let me show you a few key statistics. The CPU was quad core, as I said, a Cortex A53, 16-bit, 32-bit, and the GPU was an Adreno 308, which you can, and then you have SD RAM, 32-bit bus to connect everything. The GPU was remarkable already for this Adreno. It claimed that it had sort of like well, 6 pipes, or what you will see if you Google it, like 24 signals that it can process in parallel through what is called not a core, but sort of logical unit, an arithmetic and logical unit, an ALU as it's called. So the phone is also H.264 encoding, decoding. It did the newest standard H.265 HVC. It is only 8-bit decoding of that signal. It's one of the reasons why that phone is no longer up to date. Did I forget anything? No, you see how simple the phone is. These are nice things also, which you can see here. The antennas for Wi-Fi and Bluetooth, general GPS signal that works with the European GPS signal, GLONASS, and the Baidu system in China. So a main antenna, of course, for the phone signals itself, and etc. etc. Any case, I was happy when I opened this up and said like, hey, and I could put it back together, breaking it down in components and seeing like that's how it works. Now, I said this is a phone, a simple phone, 10 years ago, 28 nanometer technology. I want to say a few things about the chips and boards here and this incredible progress that was made, as you can see in this illustration of Moore's law from, how many transistors can you put on a microchip? It sort of doubles every 2 years. What we've seen with this new AI processing unit, I would say, from Nvidia. I'm talking about this one here. It's a unit. It has 8 B200 GPUs. It has a CPU. I think it's actually an Intel CPU. In any case, you can configure it, and it costs about $500,000. But it does indeed, process. Well, I think each chip has well, it processes petaflops instead of teraflops, and each CPU has, not a few billion transistors like these 28 nanometer chips have or had in my mobile phone, but 208 billion transistors. I'm not sure if that's combined. I think it's a combination of I will talk about it, 2B200 that are combined, because there's a thing that you need to understand. The density of transistors, how many transistors are there per square millimeter, is an important factor, because one of the constraining factors is the die size. Snapdragon 845, which is much more advanced than the Adreno chip that I have here, is sort of let's say 80 to 100 square millimeters, so a centimeter by a centimeter. This indeed, that size. And Nvidia H is gonna be like 814 square millimeter. I'm very precise because it's apparently sort of a limit that TSMC hits. And I will talk about that limit. But that's sort of a chip which is, 10 times the size, and that's expensive to produce. There can't be any defects, etc., etc. But I said that's one limit that you're hitting, sort of the size of your chip, the die size, which now is probably, indeed, that 840 square millimeters seems to be some kind of magical limit. And then sort of, I want to say something about Moore's law. Everybody thinks like, we go to 2 nanometer. 2 nanometer, I want to put it into perspective. In the end, we are talking silicon crystals that are being doped with and form then a semiconductor. I'm not going to expand on that. You can read in the papers. But I want to remind you of the fact that a one silicon crystal cell, the size from here to there, is about 5.42 angstrom. And that's 0.6 nanometer. So, like when we're talking 1 nanometer or 2 nanometer, it's clear we're talking engineering at the scale of individual crystal cells, and that's sort of a physical limit you can't go about already now. I mean, since with very large scale integration, there are clearly physical limits to how far you can miniaturize. If you have electrons traveling through this material, you have the problem what is electromigration. That is the Coulomb forces between an electron, which is negative, and a positive ion in such crystal, are such that the electron might literally tear an ion out of out of one cell and bring it into another cell. So you have the material itself starts, I wouldn't say fall apart, but its structure alters, and so that causes failure. So there's gonna be a limit on nanometer technology as such on engineering. It's really the engineering, the nanometer limit. Feynman said that 30 years ago we can do nanometer engineering. That's the scale of atoms and molecules. Well, molecules, I would say, atoms are at the picometer scale. Um, well, no, that's not correct. It's the nanometer scale as well. Atoms, the electrons, and the protons are at the picometer scale. But in any case, there's a limit there, and so what you only can do is be inventive and design like 3D MOSFETs, what is happening now, and then indeed increase the scale of your die size and other engineering feats. Let me go back to that law of more and show you where we are. So I'm lucky. You can see I was born in 1969. I started playing with computers around 1980 with these very first Intel. Well, they were invented then, but then in the 1980s, mine was an Intel 8068 that was used in the first IBM PC, and a bit before the Motorola 6800 is probably comparable to what was in my Commodore 64, the first affordable home computer, which also had a video card which revolved in. We are now 2016 8. I said transistor count is 5 billion, 3 billion, and now we have this 208 billion transistors on the new Nvidia AI, how shall I call it, processing unit. So let's go back to that one and talk about it a little bit. For that, I'm going to take the notes I took, which are here. The NVIDIA story, they have this annual event, the GTC conference, which is actually seen as an AI conference, although GTC is GPU Technology Conference. They held one this year. They're going to hold one next year. I believe there was a break before this one. And that sort of that was the big event that made the Nvidia shares explode. Apparently, they move very fast. They call it AI superchips. But actually, these do consist of GPU, of course. But it's we're talking about a microarchitecture. A system on a chip, and this new super chip about what we're going to talk now, Blackwell. It comes basically as 2 Blackwell GPUs plus a CPU, which is necessary. GPUs don't operate without a CPU, controlling the overall logic of the workload they have to execute. They go fast. I saw that. I mean, not so much, but they had Hopper now. They have Blackwell. I think next year there's a new one. The thing to note is that the technology that these super chips are produced on are called 4 nanometer technology. Maybe they will have a 3 nanometer technology, but it's not like that TSMC has a monopoly on these advanced processes. Samsung is a semiconductor manufacturer, Intel as well, and they have similar advanced processes. So you may want to look at competitors of both Nvidia and TSMC, seeing if they can develop similar products. Um, just to say that 4 nanometer technology, there's various ways why it's called 4 nanometer, but it has not that much to do with really the width of a transistor gate or a connection that is being etched on the silicon. Because as you can see, these are like of the order of 30 nanometer and 50 nanometer. I know that here. It's really about the density and new techniques to increase the transistor density per square millimeter of such a chip, and then going into the three-dimensional. I talked about this limit of 814 square millimeter. I'm not too much in the technical things, but that's apparently the limit or the biggest die you can make. It's the theoretical limit, I read, of semiconductor fabrication. So to get around that, because the Hopper technology was based on that, is that and that was a stroke of genius probably, is that Nvidia has developed a technology to pack two of these reticles, I would say, two 814 millimeter square millimeter chips into one package using I don't know the details of it, but it's called Nvidia High Bandwidth Interface, and it works on the NVLink protocol. Is that right here? So that's new, and that sort of doubles for each Blackwell probably the capacity in comparison with the Hopper. So you have a dual die package packing, as I said, 208 billion transistors now. Significant is the power consumption of such a thing. It's a 700, I think, to 1,000 watt for the B200, 700 for the B100, and 1,000 watt. And that's sort of where you can make a meaningful comparison with your the new generation of mobile phones, which are powered by GPUs like the Snapdragon 8, 10 to 15 watt, which is a lot more than the 1 watt or half a watt that my old Galaxy J2 would consume. So you're talking about a lot of power, and I said a lot of power is probably indeed also one of the many measures that you can have roughly to say like how many operations per second can this thing do. It goes up with the clock speed, which is gigantic. It's terahertz instead of gigahertz. So yeah, it goes up. Now, what I want to say in this video is that the price of these things is also something. One B200, I googled a little bit, but Snapdragon 8 Generation 4 is going to cost you a few $100s, right? A B200 is about 30,000 to 40,000 K, and with one such chip, you can't do much. You can't put it into a system. You need a B200 or a B100 system, which I showed here. The DGX unit, which has 8 GPUs, but also a CPU, the buses, the dynamically accessible RAM, lots of it, gigabytes, terabytes, sorry. But you need to buy a unit like that. And now, when you look at a unit, this was announced in just a few weeks ago. Apparently, such system is being priced at 515,000 US dollar and upwards. And the first batch of these AI system units was delivered to OpenAI, and they're going to probably put it in their data center and use it for training, much faster training. I'm not going to talk too much about it. I said the system has 8 Blackwell GPUs, a Prime CPU, and actually an Intel CPU. It has 4 terabyte internal memory. All very, very, very fast, very powerful. But the big question I want you to ask yourself, and I'm not through with this because I'm still working, is we're looking at a performance here, which is obviously subliminal, and but we're also looking at price. And so what you want to do when you invest in a product, is look at the price performance ratio, and this is probably should you make you think like is Nvidia the TSMC story, that beautiful alliance and these new incredible design, which apparently cost billions of dollars to design this thing. It is clearly a quantum leap, I would say, in well, chip technology. It is the new super chip, but I would wonder when you start expressing prices like that in some kind of a performance unit, like indeed you measure it in teraflops. You need to standardize it. Is it a 16-bit floating point or 32? So you measure in teraflops, and then I would like to see if you break down like $515,000 and you see the teraflops, the load that this thing can handle, a very specialized workload, as mentioned, an AI workload or yeah, image processing or whatever. Not sort of your standard transactional workload that you have for a financial or an administrative application. Then I wonder really like yes, this Nvidia story. Is it gonna last? For sure, it's gonna last technologically. But yeah, the boom of its share price, that's something else. And I would surely, as said, not think that this is sort of a story where one new competitor, like Apple a long time ago, simply destroys the competition, and the competition never has a chance to come back. I think it's good there is competition, and yeah, I said Samsung and Intel, they have similarly advanced processes. Probably they will link up with maybe a Qualcomm, a chip designer, and probably invent super chips that have the same performance, or maybe a bit less, or maybe more, but will probably be a lot cheaper to manufacture, and maybe be also more power efficient, because that's kind of a hungry thing. So that's gonna be it for my little lecture. I'm at half an hour. Wow. I hope you enjoyed this. I said my thing was just sort of to make sure you understand that this revolution in with these super chips, the architecture is not that different from what we've seen over the past 10 years, where GPUs become more important, or at least and work together, but still have to work together with the CPU. It's not that different, the architecture, and these are new micro architectures, of course, the way they are integrated on these super chips, but it's not new, or I would say it's not like what you hear about new quantum computers, which I think that hype has gone a little bit. It's still yeah, it's still silicon, and it's still about engineering, hardware acceleration, building a dedicated chips for very specific workloads, and becoming better and better at that. So to follow what is happening becomes more and more complicated, but it's surely not impossible. And with that optimistic message, I will leave you and upload this, and maybe I'll do it tomorrow because it's probably a bit of a ramble. But I hope you enjoyed it. If you did, let me know. Thank you.